Hello everybody, I am Dr. Punyadarshini Poonam Tripathi, Associate Professor in the Department of Agricultural and Food Engineering, IIT Kharagpur. So, we will be discussing the module that is recent invents in non-thermal food processing. In my previous lecture, I have discussed about the status of non-thermal food processing technologies around the globe. However, it was observed that there is certain limitations of the non-thermal food processing technologies in terms of their higher initial investment cost or installation cost, and there are some adverse perceptions of the non-thermal technologies also. So, in this context, some recent inventions in non-thermal food processing technologies are being studied. So, in order to discuss about this particular lecture, some of the references from books and journals are being listed over here. Now, coming to the recent invents in non-thermal food processing technologies, these are still under research and developmental stage, and they require greater attention for proper implementation of these technologies in the respective food industries. And some of these technologies are cold plasma, ionizing radiation and pulsed light technology. So, these are some of the recent invents in food processing sector. So, apart from these technologies, some of the emerging technologies can be utilized in combination, so that they can provide the maximum benefit as compared to the individual non-thermal technology, and this approach is also known as HODL technology, which also we will be discussing. So, first one is the cold plasma technology for food processing and preservation. So, cold plasma, as the name suggests, plasma. So, we know three states of matter: solid, liquid and gas. So, plasma is basically a fourth state of matter beyond solid, liquid and gas. So, this development of plasma, this is a newer technological intervention for ensuring the quality and safety of food. Plasma generally refers to the partially or wholly ionized gas that can be produced by the exposure of a gas mixture under different pressure conditions using different electrical discharge sources. The highly reactive gas species produced by the electrical discharge is thus known as the plasma, that contains electrons, photons, ions, free radicals and atoms in their parental or excited state and possesses a net neutral charge. And plasma can be categorized on the basis of the method of generation. They can be categorized as equilibrium or thermal plasma and non-equilibrium or low temperature or cold plasma. So, plasma basically can be classified as thermal plasma and low temperature plasma. So, low temperature plasma again can be classified as non-equilibrium plasma or cold plasma, and quasi-equilibrium plasma, where the temperature ranges from 100 to 150 degree centigrade, and in cold plasma temperature range of application should be below 60 degree centigrade. Coming to the cold plasma technology, because in food industries this cold plasma technology is widely employed for handling the microbial destruction. The cold plasma technology uses electrical energy which should be applied with the help of electrodes on carrier gases like oxygen, nitrogen or helium. A plasma generation system basically consists of carrier gas, suitable power sources and special electrodes, and as can be seen, this is a mechanism shown for the generation of plasma. So, here the electrodes are being shown over here, and when high electrical energy is applied to the air that is passed between these electrodes, this is the air inlet section where the air is entered into this electrodes. So, when high electrical energy is applied to these gases, that are passed between these electrodes, ionization of air takes place, and that leads to the generation of plasma. So, plasma basically starts as a short lived discharge visible as a spark, consequently it turns into high current hot arc at higher powers, and the air can be held at atmospheric pressure or at vacuum. So, coming to the microbial inactivation mechanism through cold plasma, the lethal effects of plasma on microbial cell is due to the interaction between the cell and the plasma ions, and that mechanism is known as etching process. So, high intensity radical bombardment occurs on the surface of the exposed microorganisms by the generated plasma. This in turn causes lesions due to accumulation of electrostatic forces on the exterior of the cell surface. These lesions cannot be repaired quickly by the microorganisms, which ultimately leads to the destruction of the living organism. The highly reactive species like singlet oxygen, ozone, superperoxide, hydrogen peroxide and nitrous oxide along with ultraviolet radiations, they act on the microbial cells, break the chemical bonds and damage the DNA while interacting with the cell membrane. So, this is very important. Some of the very important reactive species, they are interacting or act on the microbial cells, damaging the DNA, and then that leads to the destruction of the microorganisms. Application of this cold plasma technology in food processing sector we can discuss over here. So, the plasma treatment has been investigated successfully for microbial decontamination in case of food and packaging materials. For example, Escherichia coli in fresh produce, Erwinia carotovora in potatoes, Listeria monocytogenes from aluminum foils, paper cups and plastic trays. CP technique is basically claimed to be a rapid, waterless, zero contact and chemical free tool for pathogen removal from food contact surfaces. Cold plasma technology also facilitates microbial inactivation and surface decontamination of almost all food items like meat, poultry, dairy, freshly harvested horticultural produce and also in sprouted seeds. The next invent in non-thermal technique is the food irradiation or the irradiation of food materials. The irradiation technology or the ionizing irradiations basically are used for destruction of microorganisms during the processing of food materials. Irradiated foods are those that have been treated with ionizing radiations. This process is a physical treatment in which food materials are exposed to direct action of electromagnetic rays in order to ensure their quality and safety aspects, and this also leads to extend the shelf life of the food materials. The ionizing radiations in the form of electromagnetic spectrum with radio waves and high energy X-rays and gamma rays are also coming under these ionizing radiations. The irradiation sources that are permitted for use in food processing are the gamma rays produced from the radioisotopes cobalt 60 and caesium 137, which is a spent fuel from the nuclear reactors. The treatment received by the food product is characterized by the irradiation dose. The amount of irradiation dose decides the treatment time given for the food materials, and this irradiation dose is measured with the help of an instrument known as dosimeter. So, dosimeters are used to decide the irradiation dose that should be given to a particular food material to destruct the target microorganism. So, the international unit of measurement of irradiation is Gray, and 1 Gray represents 1 joule of energy that is absorbed per kilogram of the irradiated product. This is very important. With respect to this irradiation dose, the treatment of the food materials are being accomplished. For example, the irradiation dose less than 1 kilogray is used for inhibition of germination, disinfections, and it helps in delayed ripening process also. Within 1 to 10 kilogray, it is used for shelf life extension and elimination of pathogens. And for sterilization process, the irradiation dose from 10 to 50 kilogray is normally used. The biological effects of irradiation basically creates the damage in the genetic material of the cell, causing a lesion of the DNA followed by the breakage of both strands of the DNA. So, this damage prevents the multiplication and randomly it inhibits the cell function, resulting the ultimate death of the cell. The sensitivity of microorganisms to irradiation is based on the size of their DNA and the rate at which they can repair the damaged DNA. A schematic sketch of the food irradiation process is shown over here. As can be seen, for irradiation treatment, initially the fruits or vegetables has to be properly washed inside the chamber. This is a washing chamber in which the food materials are properly washed and cleaned to remove any surface dust or dirt that are adhered onto their surface. Then these food materials are passed into a palletizer. So, in the palletizer they are stacked together in aluminum containers and afterwards they are conveyed through overhead rail into the irradiation chamber, which is normally made up of lead. So, inside the irradiation chamber, the food materials placed inside the aluminum containers are loaded, and then in the irradiation chamber, the irradiation source, which is basically cobalt 60, is normally present in deionized water, and it is present at a depth of around 20 feet below the floor of this irradiation chamber. So, below the floor of this irradiation chamber up to 20 feet height, there is a pool of irradiation source, that is cobalt 60, that is present along with deionized water, and then the untreated containers are lifted down into this irradiation source chamber, where they will be treated for sufficient time period. Basically, the treatment time is around 30 to 60 minutes depending on the depending on the irradiation doses that are being provided for sufficient destruction of microorganisms. So, with the help of a hoist mechanism, the untreated containers are being lifted down into the irradiation source, where they will be treated properly, and after that they will be depalletized inside a depalletizer, and the containers again are used or passed into the packaging device, where the treated food materials are packaged and then they can be distributed. After packaging or during the packaging process, it is very important to provide a logo for the on the top of the food package, and this logo is known as the Radura logo, which is used to show that the food has been properly treated with ionizing radiations. So, this is international symbol of the Radura logo that has to be provided on the top of the food package, so that it is ensured that the food has been properly treated with ionizing radiation. Similarly, according to US FDA symbol, this is the Radura logo, which is showing the treated food materials with ionizing radiations. Some of the applications of food irradiations are in terms of its use for delaying the ripening process and for inhibiting the sprouting process. So, irradiation technique can be used to alter the biological processes such as delay in ripening and or senescence in order to improve the shelf life of the food products. The influence of irradiation on the ripening delay basically depends on the time gap between the harvest and the irradiation treatment that is given. What is the time gap between the harvest as well as the treatment time? The physiological state of the fruit and the sensitivity of the fruit. So, depending on these parameters, the irradiation process efficacy has been decided. Irradiation also increases the fruit respiration immediately after the treatment, but delay the time to attain the climacteric respiratory peak. Now, coming to the sprouting inhibition, sprouting of tubers and bulbs during storage is one of the major factors contributing to qualitative and quantitative deterioration during the storage period. So, sprouting inhibition by irradiation is one of the most effective technologies and it could be achieved at doses from 0.05 to 0.15 kilogram. So, inhibiting the sprouting process with the help of irradiation technology can be achieved with doses, that is irradiation dose between 0.05 to 0.15 kilogram. Our next technology is pulsed light technology. So, this is one of the very important non-thermal technology where it involves the use of inert gas flash lamps that convert the short duration and high power electric pulses into short duration high power pulses of radiation within the frequency region of ultraviolet, visible and infrared light. Pulsed light technology can be used for a wide range of applications including the rapid and effective purification or sterilization of food materials. In the food industry, basically this PLT technology or pulsed light technology is applied to sterilize, sanitize or reduce microbial load in food materials. Also is used in food packaging as well as surface decontamination, in environmental protection, plants, devices and media that are involved in food processes. The electromagnetic radiation that is emitted and propagated by means of waves are characterized by the wavelength, frequency and energy. So, the term light basically refers to the radiation in which the wavelength ranges from about 100 to 1100 nanometer and that is again subdivided into ultraviolet rays, visible light and infrared rays. So, in ultraviolet rays this wavelength ranges from 100 to 400 nanometer, which can again be roughly subdivided into UVA, UVB and UVC. Ultraviolet rays can be divided as ultraviolet region A, where the wavelength ranges from 315 to 400 nanometer, UVB region B, where wavelength ranges from 280 to 315 nanometer and UV region C, where the wavelength ranges from 200 to 280 nanometer. And also there is one vacuum UV, where the wavelength ranges from 100 to 200 nanometer. Now, coming to the visible light, here the wavelength ranges from 400 to 700 nanometer and in infrared rays it ranges from 700 to 1100 nanometer. So, there is a huge range of this wavelength which helps in classifying the ultraviolet rays, visible light and infrared rays. So, coming to the principle of pulsed light technology. So, light basically can be emitted from different sources by different mechanisms through the spontaneous transition of some atoms from an excited state to a condition of lower energy. This energy is released in the form of discrete photons and this can be given as E is nothing but equal to HF, where F is the frequency and it is again represented in terms of Hc upon lambda. H is basically the Planck's constant, C is the speed of light in vacuum and from this relation we can see that the lower will be the frequency range, higher will be the energy. Okay. So, based on this principle, as we can see, we are going to apply this pulsed light technology to destruct the microorganisms in food materials. So, suppose we have a food block over here, we assume it as a food block and the surface of the food block which is neither totally transparent or fully opaque. Okay. So, here the incident radiation is falling on the top surface having energy E naught. So, some part of this energy is reflected back, that is reflected radiation is a part of this energy that is incident, and that is in the form of R E naught, where R is designated as the reflection coefficient. So, the rest portion is transmitted energy, and this transmitted energy is moving into the inside matrix of the food material, and some portion is again absorbed inside the food material. So, the energy, that is transmitted energy, designated as E x, because up to a depth x we are analyzing this implication of the transmitted energy. So, the energy E x of light, that is transmitted to a distance x below the surface of the material body, it decreases with the depth, because this transmitted energy gradually decreases with increase in the depth of inside the food matrix. So, according to Lambert-Weir law, E x is represented in terms of 1 minus R, R is the reflection coefficient into this is the incident radiation energy. Basically, this is the incident radiation of energy into e to the power minus k x, where k is the extinction coefficient that measures the transparency or the opacity of the material for a given wavelength. Most solids are opaque and do not transmit radiation, whereas many liquids and all gases are transparent and do not absorb any energy. So, these are some of the special cases when we consider in general the solids, but here if we are discussing about the food solids. So, the energy E d, that is absorbed by a layer of depth d below the distance x, because this is up to distance x, and then the absorbed energy is within this depth which is beyond this distance x. So, the energy E d, that is absorbed by a layer of depth d below the distance x, is given as E d is equal to E x into 1 minus e to the power minus k d, where k already we have discussed as the extinction coefficient and d is the depth, penetration depth below x. So, the absorbed light energy is generally dissipated as heat, resulting in increasing the temperature of the food material, and that is given as delta T is nothing but equal to E d absorbed energy at a depth d divided by rho density of the food, Cp specific heat capacity of the food material, A is the surface area and D is the depth. So, this delta T, that is the temperature difference or the temperature gradient between the outer and the inner layers of the food material. This delta T basically it creates the temperature gradient between the outside and the inside of the food material, and that gives rise to conductive heat transfer within the food matrix. This increases the rate of heat transfer and the material temperature, which ultimately depends on the intensity and duration of the incident radiation and on the thermal properties of the food material. That means, the increase in the rate of heat transfer, this is the conductive heat transfer, and the temperature of the material, this particularly depends on the intensity of the incident radiation as well as the duration, up to what time period we are incidentating the radiation onto the surface of the food matrix, and it also depends on the thermal properties of the food material. Now, coming to the pulse light system for food material, the pulse light system basically comprises of electrical unit that provides the high power electrical pulses, lamp unit, basically xenon lamp is used that converts the electrical pulses into high power light pulses. Then a treatment chamber is also needed, where the power is delivered to the food item that has to be treated, and some auxiliary parts such as data acquisition system, control and cooling systems are also attached in the PL system. So, these are two types of pulse light systems for processing solid foods as well as liquid foods. So, in the pulse light system for solid foods, as can be seen, we have a treatment chamber and the food materials are placed on this shelf, which is normally a transparent shelf, and flash lamps are provided on either one side or both sides of the walls of this chamber, so that they directly put the light or employ the light on the food materials that are placed on a transparent shelf, and accordingly the sufficient destruction of microorganisms can be achieved. Now, this is a batch type system. For continuous type system, there is a movement, basically there is a relative motion between this flash lamp and the food product, so that sufficient destruction of microorganisms can be achieved by regulating the treatment time and the light pulses that are being provided on the food surface. Similarly, coming to the continuous pulse light system for liquid foods, as can be seen, we have a product circulation pump through which food materials are passed inside a treatment chamber, and this is a treatment chamber where the surfaces all surfaces are reflective surfaces, and flash lamp is provided over here when the food material is passing from one end to the other end of this treatment chamber with sufficient flow rate, because flow rate has to be also regulated properly depending on the treatment time. So, depending on the treatment time inside the treatment chamber, the flow rate of the liquid food has to be regulated properly, so that the suitably processed liquid food material can be liberated out from the outlet end. So, this is just a schematic sketch of these PL systems for solid and liquid foods. So, the mechanism of microbial inactivation by this pulse light technology employs the combination of photochemical mechanism, this is very important, that involves the lethal effects of light pulses on some constituents of microbial cells, and photothermal mechanism. So, photochemical mechanism and photothermal mechanism altogether aids in the destruction of microorganisms in pulse light technology. So, in photothermal mechanism, the energy of the light pulses dissipates as heat, causing a lethal increase in the temperature. The energy rich UV photons are mostly absorbed by highly conjugated carbon-carbon double bonds in proteins and nucleic acids. So, this absorbed energy is able to break organic molecular bonds, hence causing structural alterations in the DNA that leads to the destruction of the microorganisms. Now, coming to the next aspect of investigation, that is HODL technology, because the commercial application of these non-thermal technologies when applied alone or individually are only partially able to replace the conventional thermal processes to meet the overall objectives of food preservation. None of the non-thermal processing technologies alone are sufficient enough or adequate enough to achieve the commercial sterility, as resistant spores of some species are found to survive after the treatments. For example, in high pressure processing, by providing only high pressure, the microbial spores are not getting destroyed, which can be only possible with thermal treatments. So, in that regard, high pressure along with temperature integration is preferable over non-thermal alone. So, in this regard, the HODL concept is coming into picture. This is generally known as combined methods or combination technologies for food preservation, and has become a promising technology that simultaneously reduces the loss of nutritional and sensory qualities and also improves the safety aspect of the food products. Leichner and Goris in 1995, they introduced the term HODL technology, and due to the consumers growing demand for fresh, natural and minimally processed food products, HODL technology is well investigated and still has to be explored in this direction. So, the principle of HODL technology basically lies in preservative factors or HODLs that are used or basically employed to disturb the homeostasis of microorganisms. Preservative factors basically prevents the microorganisms from multiplying and causing them to remain inactive or even die. So, the Hodel concept basically illustrates that complex interaction of temperature, water activity and pH are three major important parameters for ensuring the microbial stability. Some combination technologies that can be used as Hodel approach are given. So, in HPP, the inability of HPP alone to ensure complete destruction of bacterial spores can be achieved by mild pressure assisted thermal sterilization process that relies on thermal expansion generated pressure and pressure assisted thermal sterilization, in which heating is applied before HPP treatment, and that has been proven to be effective for inactivation of microorganism and microbial spores. Combination of HPP and ultrasound with mild heat treatment were also been proposed for microorganism destruction or reduction in food products. Heat assisted HPP around pressure of 600 megapascal and temperature from 70 to 75 degree centigrade ensured better bacterial and mold spore inactivation than thermosonication and heat treatment alone. So, significance of Hodel technologies are it leads to improvement in product quality and microbial safety, save money, energy and several other resources related to the processing of the food materials. And with the application of Hodel technology, the food remains stable and safe in terms of retaining high sensory and nutritive components, because gentle process parameters are used for Hodel technology. So, it leads to the manufacture of new products according to the need of the processors as well as consumers, because in this Hodel technology regard more research and studies has to be investigated so as to come out with integration of thermal and non-thermal technologies for getting better food materials for wider publicity and commercialization of the technologies. Thank you.